These two sentences use completely different words. One says, forgot my password. The other says, reset my login credentials. But as humans, we immediately understand that they are talking about almost the same thing. Now the question is, how does an AI system know that? AI doesn't understand words the way humans do. It turns them into numbers. And this one idea called embeddings is behind semantic search, recommendations, RAG, image search, clustering, and a lot of modern AI. Hi, welcome back to my channel, and if you're new here, welcome. My name is Anna, and on this channel I explore machine learning concepts in a simple and intuitive way. If you enjoy this kind of content, consider subscribing and feel free to leave a like and a comment so that more people can see this video. Let's get started. Whenever you search by meaning instead of exact keywords, embeddings are probably involved. Whenever a recommendation system says, people who like this also like that, embeddings might be involved. Whenever a chatbot searches through your documents before answering, embeddings are often involved. And once you understand embeddings, a lot of modern AI stops looking like magic and starts looking like geometry. So in this video, we are going to understand one simple idea. Embeddings convert things like sentences, words, images, or documents into vectors, where similar things are close together. That is the whole concept. But this simple concept is extremely powerful. Let's start with a very simple example. Imagine we have these 5 words: cat, dog, car, truck, and banana. Now, if an AI system wants to work with these words, it cannot directly work with the raw text in the same way we do. To a machine, a word cat is just symbols, so we need a way to represent the meaning of each word numerically. That is where embeddings come in. An embedding is just a list of numbers, a vector. But the important thing is not the numbers themselves. The important thing is that the numbers are learned in such a way that similar meanings have similar vectors. Now, real embeddings usually have hundreds or even thousands of dimensions, but we cannot draw 768 dimensions on a screen. So let's imagine a simple 2D version. In this fake 2D meaning space, cat and dog should be close together because they are both animals. Car and truck should be close together because they are both vehicles. And banana should be somewhere else because it is a fruit. That is the intuition we should remember. An embedding is like the coordinates of meaning. Just like a city can have coordinates on a map, a word or sentence can have coordinates in meaning space. And once we have coordinates, we can do something very powerful. We can measure distance. If two vectors are close together, we say they are similar. If they are far apart, we say they are less similar. So the question becomes, how do we measure close? One common method is called cosine similarity. The intuition is simple. If two vectors point in a similar direction, their cosine similarity is high. If they point in very different directions, their cosine similarity is low. So instead of asking, do these sentences share the same words, we ask, do these sentences point in the same direction in meaning space? That is what makes semantic search possible. Now let's make this real with a small Python demo. The goal is not to build a full search engine. The goal is to see the core idea working. We will create embeddings for a few sentences, then compare a new query to those sentences and find the most similar one. I'm going to use a sentence embedding model. This model takes a sentence and converts it into a vector. Here we load a model called all-mini-LM L6v2. You don't need to worry too much about the model name. For this video, just think of it as a function that takes text and returns vectors. Now we create a list of sentences. Some are about passwords and login, some are about animals, some are about vehicles, and one is about a banana. Then we pass these sentences into the model and get embeddings. This output means we have 7 sentences and each sentence is represented by 384 numbers. So every sentence has become a point in a 384-dimensional meaning space. That sounds abstract, but the idea is simple. Each sentence is now a vector. And because it's a vector, we can compare it with other vectors. Now we create a query. I cannot access my account. Notice something important. This query doesn't say password. It doesn't say login credentials. It says account. So a normal keyword search might not immediately know which sentence is most related. But an embedding model can compare the meaning. And now we see the result. The most similar sentences are the ones about passwords and login credentials. Not because they share the exact same words, but because they live close to the query in meaning space. This is the key idea behind semantic search. Instead of matching exact words, we are matching meaning. And that's why embeddings are so useful. They give us a mathematical way to compare meaning. Let's also create a quick 2D visualization. Remember, the actual embeddings have many dimensions, but we can project them down to 2 dimensions so we can draw them. This is not the original meaning space. It's just a simplified 2D projection, but it helps us see the intuition. Sentences with related meanings tend to appear closer together. The password sentences form one small group. The vehicle sentences are closer to each other, and this is exactly what we want from embeddings. Similar things should be close. Different things should be further away. Notice that the animal sentences may look further away from each other in this 2D plot. That is because PCA compresses the original 284-dimensional vectors into only 2 dimensions. So some distances can be distorted. The plot is useful for intuition, but the cosine similarity scores from the full embeddings are the more reliable comparison. And by the way, if you haven't seen my video on PCA, I highly recommend checking it out. Now that we understand the core idea, let's look at why embeddings show up everywhere in modern AI. The pattern is almost always the same. First, take something, a sentence, a document, a product, an image, a user profile, convert it into an embedding. Then compare embeddings. That simple pattern powers many systems. For semantic search, we embed the user's query and embed all the documents. Then we return the documents whose vectors are closest to the query vector. That means the search engine can find results based on meaning, not just exact words. For recommendations, we can represent users and items as vectors. If your vector is close to a certain movie, product, or song, the system might recommend it to you. For RAG, retrieval augmented generation, embeddings are often used to find relevant chunks of information before sending them to a language model. So, when a chatbot answers questions about your own documents, it may first search through your documents using embeddings. And embeddings are not just for text. Images can also be embedded. That is how systems can match an image with a text description or search for images using natural language. So embeddings are not one small trick. They are a general way to turn unstructured data into something we can search, compare, cluster, and retrieve. But we should also be clear about the limitations. First, similarity doesn't always mean truth. These two sentences are very similar in meaning. They talk about the same topic. They have a similar structure, but one is true and the other is false. So an embedding can tell us that two things are related, but it doesn't automatically tell us whether something is correct. Second, embeddings can encode bias. If the data used to train the model contains biased patterns, those patterns can appear in the embedding space. Third, embeddings don't understand like humans. They are useful mathematical representations, but we shouldn't confuse vector similarity with human understanding. And finally, embedding quality depends on the model. Different embedding models can produce different results. Some are better for short sentences. Some are better for documents. Some are better for code. Some are multimodal and can handle text and images. So embeddings are powerful, but they are not perfect. They are a tool. And like every tool in machine learning, we need to understand what they are good at and where they can fail. So let's summarize. An embedding is a vector representation of meaning. It takes something like a word, sentence, document, image, or product and places it into a space where similar things are close together. Once meaning becomes a vector, we can compare it. We can search it, we can cluster it, we can recommend with it, and we can retrieve relevant information for AI systems. That's why embeddings are one of the most important ideas behind modern AI. They turn meaning into geometry. And once something becomes geometry, we can build systems with it. If you haven't seen my previous videos, I highly recommend checking them out. I cover topics like KNN, principal component analysis, and linear regression in a similar style. If you found this video helpful, feel free to like it and leave a comment. It really helps more curious minds like yours discover the channel. If you're interested in this kind of content, consider subscribing so you don't miss future videos. As always, all the resources, including the code, will be in the description below. Thanks for watching, and I will see you in the next one. Bye!